This is the next video in the chapter on atoms, molecules, and ions. In the last video, we talked about atomic theory and the discovery of the atom, and now we're going to move on to the discovery of subatomic particles within the atom, namely electrons. So when we last talked, we had just discovered atoms existed. Small indivisible particles that were different depending on the element. So the natural follow-up question, once we know what matter is made of, is then to say, if matter is made of atoms, what are atoms made of? Because the early philosophers predicted that matter was made of atoms and atoms were indivisible, but they didn't have any actual proof. No one had ever tried to figure out what was on the inside. So experiments followed, and they were exciting and difficult and technical. And one of them in particular is famous, done by someone named Thomson. And this experiment is called the Cathode Ray Tube experiment. So I'm going to draw a rough sketch of what that looks like, and we'll talk about how the experiment worked. So a cathode ray tube is a glass tube that contains two pieces of metal called a cathode and an anode. That's all you need to know about that. And the cathode and anode were connected electrically, and a high voltage was run between them. So a lot of electricity was pumped in between these two things. This side was negatively charged, and this side was positively charged. And as you may have guessed, when you pump a lot of electricity between two pieces of metal that are close together, you get a spark. Some energy that passes between these two. So this was called a cathode ray. So first important point in this experiment. High voltage generated this energy beam called a cathode ray. And when Thomson changed out the pieces of metal used for the cathode and anode, he tried a whole range of different kinds of metals. He discovered that the cathode ray was the same. It was the same for every element that he tried. So whatever this cathode ray was made of, it was made of something that was the same no matter what kind of element and what kind of atom you were looking at. So he wanted to figure out what exactly was in this ray. And so one thing he did to look into that was using a magnet. And so magnets have a negative side and a positive side. So we'll indicate that with colors. This is going to be blue side. This is going to be red side. So we held a magnet close to that cathode ray, and he changed the direction that the cathode ray was moving. As the magnet was being brought closer, the cathode ray that was close to the magnet was deflected in direction. It was pushed away from the negative side. So let's write that down, because the scientific method is all about observations. So cathode ray was deflected or pushed away by the negative pole of the magnet. Okay, let's do a super fast review of physics, because really, this is as much physics as it is chemistry. So what do we learn about charges in physics? What happens when we have like charges, and what happens when we have opposite charges? So if we have two like charges are going to repel each other. So if you have two positive charges, they're going to push away from each other. If you have two negative charges, they're going to push away from each other. So like charges repel, or oppose, or deflect, or move away from. Those are all different ways to say the same thing. So like charges repel, and opposite charges attract. You've probably heard this before, opposites attract. And in this case, it is actually true. So if you have a positive charge and a negative charge and they come close to each other, they're going to be attracted. Okay, so knowing what we know about physics, let's go back to our cathode ray tube. We'll make it look a little bit more like a tube. How about that? All right, so we have this mystery cathode ray beam, and we have this negatively charged pole of a magnet, and when the negatively charged pole came close to the cathode ray beam, it was pushed away. And so we know that if it was pushed away, that means the charges must have been the same. They must have been like charges. So that means that our mysterious cathode ray contained something negatively charged. So cathode ray contains negatively charged things. And that was huge. We thought the atom was indivisible, and now come to find out atoms contain negatively charged things. And this was the first time that these had ever been documented. So this person got to name them, and he generated something that had a charge, which is called an ion, and he generated it using electricity, high voltage. So he named it an electric ion, or an electron. And electrons are one of the fundamental subatomic particles that make up all atoms. So that was cool. We were able to learn something about what makes up atoms. And just for the sake of completeness, he also discovered the charge to mass ratio of this particle. So we'll add that in here. 1.759 times 10 to the 11th coulombs per kilogram. So he didn't quite figure out how much one electron weighed or how much it was charged, but he came up with the ratio of the two based on measurements. So we know that there was this ray generated. It was deflected by a negative pole of a magnet, and it contained negatively charged electrons. And we also know that atoms do not normally have charges. Atoms are neutral. We know that because atoms are stable. Things that have charges are unstable and they tend to react easily. And this is not a feature of everyday atoms. And so we know that if atoms are neutral, and we also know that they have these negatively charged things, then they must have something positively charged in them as well to be a neutrally charged atom. So we know atoms are neutral. So atoms must also have positive parts. Cancel out the charge of the electron. Okay, and we'll put a line here. So a lot has been happening here. Thomson has discovered a lot, and our model of the atom has really changed. So we need to go back and update our picture log of what does an atom look like, because we now have more information about what it looks like. So let's update that. All right, here we are, 1897. Headline, Thomson discovers electron. Fundamentally changes the view of what an atom looks like. So now we're going to say we have this atom, roughly spherical, probably, neutrally charged overall, but with negatively charged things inside of it. So we'll draw in some negatively charged electrons. There's a couple. Okay, we've got a couple of negatively charged things, and we know that the rest of it must be equally positively charged. So we'll just assume that the rest of this big blob is just a big positively charged blob. They probably did not use the word blob in the official publication, but I digress. So we knew there were electrons, and we knew that the rest of the atom was positive. And this model is called the Plum pudding model, because this is something that Thomson liked to eat, and most people knew what it was at that point. If he were to name it today, he probably would have called it the chocolate chip cookie dough model, because you have a big blob of cookie dough with a couple of chocolate chips mixed in, and the chocolate chips represent the negatively charged parts, and the rest of the blob of the cookie dough represented the positively charged parts. So we learned some interesting information about an electron, but there is one more experiment that happened related to the electron, because at this point, we don't actually know the charge or the mass. We only know the ratio of the two. So we need to know how much an electron weighs as well. So the next stop in history on this time machine is the Milliken oil drop experiment. So Milliken oil drop experiment was amazingly simple enough that even I can make an attempt at drawing it. He took a container of oil and he aerosolized it into little droplets, kind of like a perfume bottle when you squeeze it, when you squeeze it and it makes lots of little tiny aerosols. So lots of little tiny droplets, not to scale, came out of there. And he did this inside of a chamber with a little magnifying glass so he could watch these particles. And so he produced these tiny particles, and then he put a charged plate at the bottom. So this was a negatively charged plate. So we'll color it blue. Here we go. And as these microscopic particles fell down towards the negatively charged plate, they were again repelled by that plate. So they appeared to slow down as they fell, and some of them were even frozen. They were hovering in place over that plate because they were repelled so much by it and because they weighed so little. So observation from this experiment, microscopic oil droplets were repelled by a negatively charged plate. And we can assume the same thing we learned up here from physics. If one thing is negatively charged and the behavior that we see is with deflection, then those two things must have the same charge. So that means that these particles also contained negative charges, but the particles were deflected by different amounts depending on how big they were. Some of them were deflected only a little bit. Some of them were deflected more. Some of them were deflected a lot. And so Millikin took that to assume that there were different numbers of these negatively charged electrons inside of these. So by measuring a huge, huge number, hundreds of thousands of oil droplets, and being very careful about how negatively charged this plate was, he was able to measure the charge on individual droplets. So the charge on an individual droplet varied, but it was always a multiple of one particular number. There was a greatest common factor. And that factor was the charge of one electron. So the charge on a droplet was always a multiple of 1.6 times 10 to the negative 19 coulombs. So he's decided that that was the charge of one single electron. So that meant if an oil droplet had a charge that was greater than this number, that it had multiple electrons attached to it. So that was pretty cool. And because Thomson up here had found the charge to mass ratio, and Millikin had found the charge, then logically he could also find the mass. So using Thomson's data, found the mass of an electron to be 9.1 10 to the negative 31 kilograms. So very, very, very light particle. So our picture is getting even a little bit more clear. We know a little bit more about electrons now. We know about how much they weigh and about how much they're charged. So that means we need to update our log of what does an atom look like with Milliken's view. There we are. So let's add Milliken, 1909. Milliken contributed the electron charge and mass. Kind of a big deal. Okay, so we have an atom, and it's a big, roughly spherical particle, and we know that it has both negative and positive charge in it, but now we know that electrons are particularly small. So the theory changed to say that perhaps electrons orbited the atom like they were on a racetrack, like the rings of Saturn, lightly and very quickly pushing around the outside of a giant positively charged blob, like before. So we have these very, very light, negatively charged electrons, and we still think there's a positive blob in the center of the atom. So you can see that our atomic view is coming along. It has charges in it now. It has a few masses in it. And in the next video, we'll talk about the discovery of protons and neutrons and how that took the picture of an atom one step further into the future.